Right. So we are showing that the following very important theorem that in R, sequence is Cauchy if and only if the sequence converges. Right. And we had shown we were showing, I think, that we were showing the forward direction, right? That if it's Cauchy, then it's going to converge, right? Can anyone sort of sketch out the idea? Does anyone remember the idea? So we split it into two cases. We said, well, no. I'll see if anybody remembers. Can anyone sort of lay out the idea? Sort of talk the strategy. It's okay if you can't, but try to, right? Try to be able to just say, oh yeah, here's the idea. Right. So we said consider. So let the sequence. So let what do we call it? A sub n be Cauchy, and let S, I think, S be the set of all values. Okay. So you have this, the set of all values of your sequence. Right? These are all the outputs. Okay. Then either S is finite or S is infinite. Right? Either you have either S has a finite number of values, like something like if A sub n, something like say 1, 1/2, 0, 0, 0, 0, 0, 0, 0, 0, right? Then your S is going to be just three values, 0, 1/2, and 1, right? Or you have an infinite number of values. Okay. Okay. And so what we started off with last time was so there's the case where S, the cardinality of S is infinite. Suppose you have infinitely many values. Yeah.
Just the example you just mentioned.
Yeah.
The finite.
Yeah.
Is it the number of elements in the sequence, or
not the number of elements in the sequence, but number of values.
Oh, value.
The values attained, right? So there are only three values there. So that's this set. This set here is the set of values attained by the sequence. Okay. And so I think one of your homework exercises was to show one that any Cauchy sequence is bounded. Okay, so we're gonna assume that. We assumed that, and then what was the key thing to do? We invoke Bolzano-Weierstrass, right? So by Bolzano-Weierstrass, for sets. Later today we'll do a Bolzano-Weierstrass for sequences, and that's actually the one that's more usually called the Bolzano-Weierstrass theorem. But the one that we had earlier, by the Bolzano-Weierstrass theorem for sets, we know that S has an accumulation point. Call it L. Right. Okay. And so, obviously we're going to take, we're going to think that's probably the limit. Right? It has an accumulation point, so we claim that L is actually the limit of A sub n. Hey, Roland.
Actually, the theorem states that there is at least one accumulation point, right? What if we say, well, there might be more than one?
Yeah. So S has at least one accumulation point.
And then how do we pick? Or we try...
Choose any, choose one. Choose one. Call it L.
Okay. But how do we make sure that exactly this one is...
Well, if we show that this sequence has the limit of L, then there could not be any other accumulation points.
Can the sequence converge to a couple of values then?
No, right? If it converges, then there's maybe you can take that as an exercise, right? If A sub n converges, then in fact S will have only one accumulation point, namely the limit.
Right.
Okay, so what we'll see is that we'll see that the sequence converges, and then it's sort of clear that there's never going to be any other accumulation point. Right? Can you see that? Can anybody sort of give a like an intuitive idea of why you can't have an accumulation point other than, suppose you have a convergence sequence. Okay, so you have a convergence sequence, right? Converges on L. Okay. Could there be another accumulation point? Why not? There can't be. Why not? Can anyone sort of give an argument? Remember what an accumulation point is? That in every neighborhood, every punctured neighborhood contains an element of the sequence. Okay. So if this is the limit, why can't this thing be an accumulation point?
You will have to, like, wouldn't the sequence converge to S2?
I guess that's one way of thinking about it. If we show that whenever you have an accumulation point, that thing would be the limit. If there were two accumulation points, then both of them would be the limit, and by the uniqueness of limits, they have to be the same. So this is sort of like using the argument in advance, right? We're gonna, okay, but suppose we haven't shown this thing over. Suppose we haven't shown that an accumulation point is gonna be the limit. Okay, and you've got nothing yet, and somebody says, well, how do you know that you have a sequence that converges to a limit? How come you can't have another place that's an accumulation point? Okay.
If you have an element that's contained within the neighborhood of S, then it can't be contained within a different neighborhood of L.
Okay, so you could say, well, let's take neighborhoods that separate these guys, right? You could say take if S and L are if L is the limit, L is the limit, and S an accumulation point, and they're not the same. Okay. They're not the same. Then take neighborhoods that separate them. Right? Take neighborhoods that separate them. You know that past a certain time, all the elements lie inside this neighborhood, right? And then inside this neighborhood, does this lead to a contradiction? Almost. Almost. To show that this is not an accumulation point, you have to find a neighborhood that has nobody in it, right? You have to find a neighborhood that has nobody in it. But can you? Past a certain time, everybody's inside here, right? Everybody's inside here. So who's not in here? Only finitely many guys, right? So just take the minimum distance between S and those finitely many guys, and you can find a tiny, tiny neighborhood that misses all those guys, right? And then that neighborhood would show that this is not an accumulation point. You guys see that? Okay, so that's the idea, right? Right. So if you wanted to write it up, I wasn't planning to do this, but if you wanted to write it up, you'd say, well, choose an epsilon that is greater than 0. Say epsilon. Choose epsilon to be, say, the distance from L to S over 3. then there exists a time such that if n is past that time, a sub n minus L, a sub n lies in that epsilon neighborhood of L. So the whole tail, passage in time, the tail lies inside this epsilon neighborhood of L, right? Then let radius be the minimum of the distance from S to A1, S to A2, S to a capital N over 2. Okay, so there's only finite, take look at the finite head, right? Look at the finite head, and you say, well, look, you know, I can take the minimum distance between S and any of those guys in the head, take half that distance, then N R S star contains no elements of the sequence. So S is not in the accumulation. Okay. I should have just given that as an exercise, as homework. Okay, I'm going to erase it.
No. Epsilon was just an arbitrary choice.
No, I chose it so that it wouldn't contain S. Right? I chose it so that it's 1/3 of the distance from L to S, so that I don't contain S in there. Right? Because I want to to get everybody away from S. Right? I'm trying to find a place where there's nobody around S. So I'm going to say, everybody. I'm going to make everybody get close to L and away from S. And then there's finitely many guys, you know, that I didn't capture, but there's only finitely many guys, so I can choose a minimum distance that misses all of those guys.
Yeah, but it can be, you can choose smaller. Well, I'm assuming why like over 3.
Yeah, so it could be over 4. It could be over. I mean, any epsilon less than this would do. Yeah, but then I have to be a little bit more careful. Yeah. Okay. Okay. Ah! Okay. Yeah, that's handy. Okay. Okay. So let me just sketch this out, right? We claim that L is the limit, right? So we know that there's this L. This L is an accumulation point, right? Well, I want somebody to try and tell me why this happens. This is a pretty important proof. Does anyone see how it works? We're trying to show that this thing is this guy is an accumulation point, right? So what does that tell you? In every punctured epsilon neighborhood, there's a guy, right? Every punctured epsilon neighborhood, there is there's some A, right? Okay. So why does that make L the limit point?
Well, we can use the fact that it's Cauchy,
Yeah.
and then use the triangle inequality.
Yes, exactly. Right. Actually, you said this last time, so right. You're trying to show that this thing is the limit. Right? What does it mean to show? What does it mean to show that something's the limit? It means that given any neighborhood, you can get everybody inside there. Right? Given any epsilon neighborhood, you can find a time past which everybody's inside. Okay. Well, let's take a neighborhood, take any epsilon neighborhood, and we say, well, I'm going to take the half neighborhood of that. I'm going to take the half neighborhood. Okay. Since this is an accumulation point, I know that there's a guy inside it. A sub k0. Okay. So take, so given epsilon given 0, take, we know there exists a k0 in the half neighborhood of L. Right? Because it's a punctured, because L is an accumulation point. Okay. But we also know that the sequence is Cauchy, right? Since the sequence is Cauchy, there exists a time past which the distance from an to an is smaller than epsilon over 2. Okay. No, actually, I should be a little bit careful here. Okay. In fact, I know that there are infinitely many guys in the epsilon over 2 neighborhood. Okay. So choose one of the aka zeros where the index exceeds this n. Okay. Choose one of these guys where the index exceeds n, and then right, for all n bigger than n, the distance of a sub n to ak naught is less than epsilon over 2. Right? Because k naught is bigger than n also. Right? Since the distance from ak naught to L is less than epsilon over 2, we're done by the triangle inequality. We've done my triangle inequality. Okay. Any questions about that? I think it wasn't completely clear last time. I wanted to say it again. Any questions? Here's the sort of cute part, right? Right? You've got infinitely many of these guys in the punctured neighborhood. Right? Since there's infinitely many of them, you know that you can choose one where the index exceeds n. Right? Your n is fixed, and there's infinitely many of the ak naughts. Well, they're not going to all be less than n because there's infinitely many of them. So one of them has to be across the line. That's good. That's what you wanted. That guy, you're going to use that guy as your base and say, well then, if n is bigger than n, you know, since that guy is across the line too, the distance between that guy and anybody else is less than epsilon over 2. But the distance between that guy and L was less than epsilon over 2 too. So a sub n is within epsilon. A sub n when L is less than epsilon, and we're done. By triangle. Okay, so there's the second part, which is now suppose S is finite. Suppose S is finite. So there's only a finite number of values. Okay, there's a finite number of values, right? And you know your sequence is Cauchy. Who can tell me what happens? What's the idea here? You've only got a finite number of values. Let's suppose we've got 3 values. Okay, right? You've got your sequence, but the sequence only takes on 3 values. V1, V2, and V3. You know, V1, V2, V3, whatever. Okay, why does that thing have to converge? This is actually really closely related to problem 2 in your homework today. This is basically problem 2 in your homework. Right? You've got only 3 values. Suppose they are integers, 1, 2, and 3. Right? Suppose you have a sequence, it's a Cauchy sequence, and it takes on only integral values. Right? Then what's going to happen? You did the homework, I think, right? Right? You do not have confidence in your homework? Yichen, say something.
You mean the sequence?
Yeah, what's going to happen?
Like series.
It'll end up something like that, right? Because it's Cauchy, it's going to end up constant after a while, right? So you say, okay, well, suppose S is finite, say S equals value 1 through value 1 through, no, let's say it this way. Suppose S is a sub n1, a sub n2, a sub nk. Okay. So there's only these values, and I've chosen like elements of the sequence that attain those k values. So it has only k values, right? Then let epsilon be the say the minimum distance between pairs of these guys, A and J minus A and K. J not equal to K. I shouldn't use K because I used it for I and J. I and J. Take 1/2 of that. Okay, so take the minimum distance, so the guys aren't integers, but there's only finitely many of them. Okay, take the minimum distance between pairs. So this is the minimum distance between pairs, right? Between any two values. Okay. Right? Since the sequence is Cauchy, right, there exists a time such that past that time, you know that a sub m, if you have any 2 elements past that time, then a sub m minus a sub n is less than this epsilon. But that means that the sequence must be constant. Right? Must be a constant value because it took on any 2 values. Those 2 values differ by more than epsilon. Okay, and so that guarantees convergence also.
What does it mean the sequence must be constant?
It will have only one value after a while. Like if your values were 1, 2, 3, then it must stay at a particular value after. The sequence must be constant after n. It's not constant throughout, but after that point in time, it's going to be constant. Okay, so okay, so that's it, right? We see that in R, any sequence is Cauchy, any Cauchy sequence converges, right? And so this is definition. A metric space, you don't know what this is, a metric space. So you don't know what this is, but I'm going to say it anyway. A metric space in which every sequence converges is called complete. And what we've just shown is that that R with a metric, that R with this notion of distance, with this notion, so metric is basically a notion of distance. Right? When you talk about Cauchy sequences, Cauchy sequences are defined with respect to a sense of distance. Okay. So what we've just shown is that with this definition of distance, R is complete. Okay. We've also seen that Q, we also saw that Q with the same notion of distance is not complete. We also have seen that this thing is not complete. And in fact, there's sort of another way of viewing this whole process. In fact, it's just for your entertainment, maybe. R is what's called the completion of Q with respect to this distance, with respect to this metric. Okay. So you can think of R, there's another way of thinking about R, which is the following. Okay. I'm just going to hold on. Okay, which is the following, that, okay, so think like this. No, I'm going to hold on. Right faster, John, you're too slow. This is important. It's kind of cool too, so I want everybody to hear it. Okay. Okay, so there's another way of thinking about R, which is the following. Q, with this notion of distance, actually has holes in it, right? Has holes in it. You've got these limits, and yet those limits approach something that isn't in the space. Okay. Then what you do is you complete Q, you fill in those holes, and you get R. Okay, so R is the completion of Q with respect to this metric, right? And this should make you have a question. What happens if you take another metric? What happens if you define a different notion of distance? Do you get something other than R? So you define a completely different metric based on something else. Okay, and you say, and maybe Q isn't complete with respect to that. Complete Q with respect to that metric. What do you get something else? And the answer is actually yes. So in fact, there are these guys called the p-adic numbers, okay, which are used in number theory.